Excellent.
You're ready.
All right. So everybody get comfortable for a second. Let's, we want to get our speaker going so that we can see this occultation tonight and get up there to see it. So I'm really pleased. I didn't think that I was going to be able to get you because you were going back and forth between Hawaii and it was all very close and touch and go, but it did work out. So again, from the Southern Connecticut State University, please help welcome Elliott Horch.
Thanks a lot, Dan. I really appreciate all the hospitality everybody has shown me tonight, so thank you very much. It's a great dinner and a great meeting that you guys had right before this. So I want to tell you a little bit about the work that I've been doing with the Kepler mission. Now, some of you may know that Kepler is a satellite that's looking for exoplanets, and its primary mission ended in 2013 because of instrument failure. But they were able to kind of repurpose the satellite, and it's now looking at things along the ecliptic and searching for exoplanets along the ecliptic. So it's not, it's kind of a really interesting second life that the Kepler satellite has had. Nonetheless, I'm going to focus mainly on the original mission in this talk. So my main collaborators in this work are Steve Howell, who's the project scientist for Kepler and for the repurposed Kepler mission, which is called K2. David Ciardi at Caltech, Mark Everett at NOAO, which is in Tucson. And then we have some younger scientists in our group, which is really nice. We got some young blood in there with Johanna, Leah, and Nick. So we have a really nice team that's working together to put together these results. So everybody knows what our solar system is all about. We have 8 planets, several dwarf planets, a G-type star. But how typical is this, and what does nature like to produce in the way of solar systems? Is ours a typical solar system, or is it in any way atypical? And also, how do solar systems in general form? So we all probably learned in kindergarten this basic picture of you take a big cloud of gas and dust. It's susceptible to something called the Jeans instability, which means basically that in order to form a planetary system, that gas has to be reasonably cold. It can't be too hot, or it won't collapse. And so, but if you do get it to collapse and there is some overall angular momentum, then essentially you form a disk of stuff, you form a star at the center, and over time, through a process which is very complicated and nobody knows in detail what it's all about, you can form larger bodies. Well, I shouldn't say nobody knows about it, but the details of how planets are formed out of this disk are complicated. I think that's fair to say.
What imparts the rotation in the first place?
Well, that the cloud itself would have some sort of rotation to begin with, right? There's rotation throughout the galaxy all the time. And so any small portion of the galaxy could have its own particular angular
local rotation, right?
Local rotation.
Like eddies in a river.
Yeah. So there's been a lot of great theoretical work that's been done in the last 10 years or so, and I really like showing this movie, which is the result of a very sophisticated supercomputer model of how stars form. So I'm going to put it in motion, and we'll see about 260,000 years of star formation happening in about a minute. So let's see if we can get that to happen. So a large gas cloud collapses. What happens is that you sort of form filaments in there. Many stars will be formed out of this. So the picture that I just showed you was for a single star forming a stellar system. This is actually going to form a little cluster of stars, which is interesting. We think that most stars form in groups, not singly. And that once the stars form, you get to see them interact gravitationally, and that's one of the things that occurs in this movie. So we see our first stars forming along this little filament. There are 2 stars that immediately start interacting, almost like a binary star system. But as there are more stars formed, then you can get some of those guys kicked out. You can have a very complicated interaction. Here's one that I like. This guy gets kicked out of the whole mess of stars being formed, and it actually forms a disk. Okay? Some other of these stars don't form disks. So already this simulation is sort of informing us about, do all stars wind up forming with a disk? And the answer might be no, because some stars get their disk disrupted through gravitational interactions with other stars that form close to that. So it's a mess, but it's kind of a beautiful mess, I think. Yeah.
Isn't it, have they yet found the companion to our star? Because we believe our star was formed this way, and so there are brothers and sisters of our G star in the local group?
Well, no, I think the answer is no. People don't know what star that might have been, or if that happened. And I'll say a few comments at the end about that. But so once you see a picture like this, and we've talked about how in our solar system we think we have some sort of cartoon of how the planetary system formed, then the question becomes, are there exoplanets? That is, are planets around other stars common? And this basically traces my whole adult life as a scientist. When I was a graduate student, that was at the time when 51 PEG was found to host an exoplanet. And there were a couple fits and starts, but the bottom line is that over the last 20 years, it has been a very exciting time, and we have answered one of the fundamental questions in astrophysics, which is, are planets common? And the answer is yes, they're pretty common. Okay, and interestingly enough, we've found this out not just with one technique, but with kind of a range of astrophysical, observing techniques, I would say. So what I'm most familiar with and have worked with over the last few years is Kepler. So Kepler is a satellite that has confirmed, just this one instrument, just this one satellite has confirmed over 1,000 exoplanets as of today. And there are thousands more that the satellite has flagged as exoplanet candidate host stars. And so what do you need to go from a candidate to a confirmed planet? Well, it's not like politics where you have a debate or anything like that. But what you have to do is you have to use ground-based techniques to learn more about the star. And if you know more about the star, then you can deduce more about whether that's a real planet or not. And so that's kind of where I come in, is I'm involved in the ground-based follow-up for the Kepler mission. So the title of my talk was as the new astronomy. So I don't know, some of you may know that when Kepler was alive, he actually published a book called The New Astronomy, which is where he published the 3 laws of planetary motion. And so it's sort of a doff of the cap to the person Kepler to title the talk that way. But now we have a satellite which is named Kepler also that has done all this great observing. So what did Kepler really do from 2009 to 2013 when it was up there with the primary mission? Basically what it did is it stared at one part of the sky all the time. And so it was a very good photometer, meaning that it could measure the brightness of stars in its field of view very, very precisely. And it would transmit that data down to the ground periodically, and then scientists would look through that, and they would look for the telltale dimming of light as a planet passes in front of the host star. So this is known as the method of transits. And so it is such a good photometer that it can go down to about 20 parts per million for a 6.5-hour integration. And if you had an Earth-like exoplanet orbiting a G star in the Kepler field, the variation in the brightness as that planet came across the face of the star would be about 100 parts per million. But of course there are systematic errors that have to be worked through, and so basically the end result is the Kepler satellite is just good enough to detect an Earth going around another star, just about good enough. And there's something on the order of a dozen or maybe 2 dozen Kepler discoveries that we would consider really Earth-like planets in the habitable zone. So this is a little picture of the Kepler field. It's a summer field, and so you can see a couple of other bright summer stars that are labeled there. So Vega is down here, and Deneb up there, Altair over here. So it's a pretty good chunk of the sky there. And as I mentioned, then the idea is that you can look for this telltale dimming of light. And so if you measure the timing of that, okay, using the little curve that we had here. So the star is uniform in brightness up to a certain point, then the planet starts to come across the disk, so that there's a trend downward, and then when the planet is on the face of the disk, it's pretty much a flat bottom there, not quite, but almost a flat bottom. But the point is that from the onset to when you're down in the valley here, if you measure the time of that and you compare it to the time of the entire eclipse, then there's a way to figure out what the radius of that planet is. Okay, just by what you really need to know. It's a pretty simple equation. If in the simplest case, it's a little bit more complicated if you don't get things aligned just quite right. But the bottom line is that you make these timing measurements, and if you know the radius of the star, then you can deduce the radius of the planet. Okay, and so you can learn something about the planet that way, which is fundamental. You can learn about the size of the planet.
And how do you know the radius of the star?
Excellent question. So we have measured the radii of stars using large interferometers, these really large instruments that are sort of in fashion these days. We have images of the disks of stars for nearby stars. So we say, oh, well, this Kepler star is the same spectral type as this star I have here, therefore they must have the same radius. But, is that really true? Because there are several parameters that go into the radius of the star. So the answer is that you better know your star very well, right? And if you know the star, you know the host star very well, then you can say something sensible about the radius within certain error limits. Okay, but it is a limitation.
Further question on it, that the ratio, you don't show time and show radius, but the ratio of the light diminished, sense light diminished, to total light, that's your parts per million?
Well, right, yeah, so that's this little dip. It could be, let's say, 100 parts per million to be safe.
So normal star luminance might lose 100 parts per million as this passes in front.
Right.
And does it take 2 passes of the same planet to assure you that it's not just a sunspot?
Right, yeah, and in fact, Kepler, I think the rule was to do 3 passes, right? So what that means is in a 4-year mission, you can get down to sort of 1-year kinds of orbital periods, right?
And
you
the
get
ones
2,
that
3,
have
or 4.
longer orbital periods are too far away from it, so you're not of interest anyway.
Well, yeah, I wouldn't say they're not of interest, but they are not detectable, in the same way as we're talking about here. So, anyway, the hard truth about Kepler is that we're talking about these little dips in light, but they don't necessarily come from a planet. There are other ways that you can get that. So let me describe one disaster scenario, or let's say that's too too negative. My wife wants me to be more positive. Here's a case where, let's say you have a Kepler star here, but in the background is another star, which by bad luck is almost perfectly aligned with the Kepler star, and it itself is actually a spectroscopic binary star. Then what you would see is a similar sort of very small dip in light, right? As the eclipsing binary goes around and it shows its characteristic light curve, but it's diluted because you're actually looking at the star, who knows, hundreds of light years in front of it or whatever. And so that's kind of where I got into this game. The one way that you can guard against that type of false positive is you can take very high resolution images of the Kepler star and determine there's no other star that's closely aligned with the Kepler star. And so, this run that I just got back from Dan mentioned, I was in Hawaii last week. I was observing using this high resolution imaging system that we built at Southern Connecticut State University. So a few words about that detection system. It's what's called a Speckle imaging system. So everybody knows, like, if you shine a laser, like a laser pointer, if you look at that laser spot on the wall, do you guys know that it's not really uniform, right? It's kind of speckly. Mm-hmm. That happens because this laser light, which is marching up to the wall like it's, so many rows of a marching band, when it hits the wall, it's a rough surface, and it's not, those aren't really, you get a sort of a corrugated wavefront coming back at you. It's not really lined up anymore because it reflected off of a rough surface. And so what speckle imaging is all about is the following thing. What happens to laser light in reflection off of a rough surface also happens to light from stars as they come down in transmission through the atmosphere due to the turbulence in the atmosphere, and that creates little eddies of different index of refraction. So anyway, the light propagates down through there in transmission, and what you get at the end result is the same thing, this sort of corrugated wavefront that enters your telescope. And so if you go to a big telescope and you look at a star, and you look at it, well, this turbulence is changing all the time, so if you take a very short exposure, then you'll see that it's speckly in the same way as these laser spots are speckly. And that's actually good in a way, because if you can see those speckles, you can see that you can see high resolution features in there. You know you've got some high resolution information to work with. You just have speckles all over the place, and you have to sort of have a way to sort that out. So this is an example of a little movie of looking at a single star through a big telescope. And so the image breaks up into these speckles, and the speckles change in location and intensity very quickly in time. So typically, if you want to do this work, you have to be taking, tens of images per second on your star, so you can see these speckles and then go forward with the analysis. So at Southern, we built a camera to do this, and it's sort of unique because it's the only two-channel speckle imaging system in the world. So instead of getting a seeing limited image of a star, like this one, what this system will do is that you split the light with a dichroic inside the camera, so that red light goes one way and blue light goes another way. Or actually, in this case, it's going to be red and green, but you get the point. And so you can simultaneously detect these speckle patterns in two different wavelengths at the same time. So instead of having this, what the camera will do is it'll give you this in the green, and then it will give you that in the red. So you actually get two high-resolution images instead of the one blurry image that you started with. And so we can go all the way down to the diffraction limit. So at Gemini North, where I was last week, the resolution or the width of these spots for a single star would be on the order of 2/100ths of an arc second. So in other words, 20 milliarc seconds. Pretty good.
That's pretty
Not too
good.
bad. Okay, so here's a picture of the camera hooked up to Gemini North. That is one heck of a big telescope, let me tell you. It is 8 stories tall. There's one in Hawaii. There's an identical twin in Chile. These are the flagship telescopes of our national observatory system, as you probably know. And so it's really funny hooking this camera up there because the camera is about the size of a large pizza box. It's a little thicker than that, so maybe it's a Chicago-style pizza box. But it's so small, and Gemini is used to such big instruments that they had to put on there, just to get the weighting right, they had to put this big cage around the instrument with huge barbell weights on either side. Because they're used to sort of VW bus-sized instruments sliding into those ports. And this is quite a bit smaller than that. But we get really great results at Gemini. So here's sort of a comparison. This is I think it's about a 13th magnitude star that we observed at a 3.5 meter telescope in Arizona. And here's the same star when you look at it at Gemini.
Boom. Wow.
So
some clarity.
Yeah, it's not only better resolution, but it's much higher signal to noise, right? Because the noise grass, it's like the grass has been mowed here. We don't have to worry about noise anymore. Before mowing the grass, that's after. So it's caught the attention of folks, and we've been able to take this instrument and use it out there 5 times now. So we have an official visiting instrument status at Gemini, which is great. So there's a lot to do, and a lot of that time gets used for Kepler-related science. So the main reasons this instrument is kind of unique are as follows. We're using state-of-the-art detectors. There are these cameras that are called electron multiplying CCD cameras. I don't know if any of you have heard of those, but
I want one.
yeah, you definitely want one. Yeah. They're awesome. So you guys have probably used CCDs many times, right? And CCDs are wonderful detectors. Well, imagine if a CCD was sensitive enough that you could detect a single photon.
Wow.
That's what these do, basically. The way they do that is that, you know, when you read out a CCD, you read your charge packets up to an amplifier. And what an EMCCD does is it basically, instead of just reading it up to the amplifier, it just slams it up through each successive pixel so the charge builds up. So that charge that you read out, even for a single photon, is higher than the amplifier read noise. And therefore you can basically do photon counting. You can detect individual photons with 90% efficiency. The silicon, for a back illuminated chip has a higher than 90% capture rate for photons. So that's one thing that we do. The other thing is we're taking data in 2 different colors simultaneously, so that's much more efficient than other systems can do. What that means is if we detect a binary star, we can actually do a color measurement of the components with one shot. Okay, so nobody else can do that. And the last thing, which is sort of a subtle point, but in some ways is the most important, is that you may know that, like, if you look off of the zenith in some direction, right, you know that the atmosphere acts like a big prism, and it spreads the light out into the colors, right? It's dispersion. And so, but if you're taking data in 2 different colors simultaneously, you actually have leverage on that. You have 2 different data points, and you can say what is dispersion, and what might be 2 stars that are blended together at the diffraction limit. So essentially, having 2 colors allows you to measure shapes of speckles in 2 different colors. That means you can actually measure the separation of binary stars that are below the diffraction limit, which means, like a Gemini, I think the smallest separation we've measured is 5 or 10 milliarc seconds.
Wow.
So it's pretty amazing, right?
Yeah,
That's crazy, man.
So it's been a successful instrument. And it's really kind of funny for me having built this, because I feel like the instrument has gone off and had its own life. I'm like the parent, I'm an empty nester, right? In June it's supposed to go to Chile. I'm not going to go to that, but it's going to go down there and take all these observations, and But anyway, it's great. So now let me kind of tell you briefly about one of the big results that has been. We've been able to sort of nail with this camera, and that has to do with this notion, going back to the beginning of the talk, of how solar systems form and how unique is our solar system, or is it a typical solar system? And so we have looked at a whole heck of a lot of Kepler stars. Some of them have exoplanets, some of them don't. But what we find is that for those that host an exoplanet, about half of those have a stellar companion. Okay, so not, so imagine you have your Kepler star, and you might have a planet or a couple of planets orbiting that star, but some distance away, sort of going back to your idea, some distance away, there's a second star in a very wide orbit around this planetary system. And so that appears to happen about half the time. And so in that way you could say, like our solar system, we don't have at least we don't know of a second star, right? People have looked hard for one, and there doesn't seem to be one. And so, but half the time there is such a star. So how did we get to that result?
Is it typically in the same plane as the planet?
Well, the answer is we don't have enough examples to know yet. And we don't have enough of a time baseline on the systems that we have to really tell you about orbital characteristics. So, but here's what we can say. Okay, so let me sort of explain the basic methodology of this result. So the idea was that we first did a little simulation. Okay, there are these websites, a couple of websites that you can go to where you can basically download a fake galaxy, which is kind of neat. So there's this one galaxy model called the Trilegal model, which basically you choose what position in the sky you want to look at, and it'll generate a fake list of stars and their characteristics in that direction. Okay, and so this is sort of perfect for what we wanted, because we were interested in things like, well, how often does a Kepler star have a background star that's within an arcsecond of it, or some, you know, some idea like that. And so, anyway, we can sort of download simulations of the galaxy, you know, pointing in certain directions. So we pointed to the Kepler Field, and I downloaded, you know, 10 different you know, galaxy simulations in those directions that were kind of randomly spread throughout the Kepler Field, and we started doing some statistics on those. Now, some of those stars are binaries, okay, and you can use what we know about binaries. There's a sort of really big paper from 2010 where the authors of that paper, Raghavan et al., they basically compiled everything we know about binary stars that are pretty close to the sun, what their characteristics are. So those are sort of embedded into this galaxy model, and so even better, because we were interested in knowing not only how many times we get a line of sight companion to a Kepler star, but how many times, you know, assuming that having a planetary system doesn't change your binary statistics, we'd like to understand, well, how many of those would be, you know, how many of those true binary stars would be detectable by our instrument. So once we had this simulation, we basically, you know, ran it through the detection parameters for the camera, and we came up with a graph which looks like this. So let me see if we can, I'm sure you can't read these labels, but this bottom label is separation. So it goes from 0 over here, that is to say, for companions, you know, let's say found in this model, you know, so sometimes you get a companion within 0.2 arc seconds, sometimes you get a companion within 0.4, etc. And this goes from 0 up to 1.2 arc seconds. Okay, so and then this axis is the magnitude difference between the primary star and the companion that's right next to it. Okay. And so there are two different, we'll talk about the colored dots in a minute, but in the background there are two different, there are open circles and then there are these filled black circles. So the filled black circles are where, you know, in the model, those are the stars that are line of sight companions in the model. And then these stars that are, these points that are open circles, those are all truly bound companions, that is, binary stars. So they're orbiting one another. Okay, and again, this is all the model that I'm talking about so far. But the interesting thing is, if I were to cut a line right down through there, something like that, can you see that basically anything below that line would be a bound companion? It would be a true binary star. And everything above that line, or most of it, would be line of sight companions. Well, this is great, because now we can tell the difference between line of sight and truly bound companions just by, you know, we can go off and observe whatever stars we want to in the Kepler field, and if we find a companion and it's below that line, more or less, then we can say that those two stars are almost certainly not just line of sight companions, but they're physically bound. And so if we already knew that the brighter star had a planet going around it, now we can say for sure that it's a star and a planet and another star which is gravitationally bound. It's not line of sight if it's down below this line, right? So this graph, in a way, it really neatly divides the two cases of line of sight and binary companions for these Kepler stars. And then I guess I should have mentioned earlier, but this red curve, that's the detection limit for the camera I just showed you when it's hooked up to the Gemini telescope. Okay, so basically it says we can get down to separations, you know, near the diffraction limit of the telescope, 20 milliarc seconds. And then if you have a companion which is even a little bit bigger than that, then we have a lot of capability to detect that up to about, you know, this is 4 magnitudes difference, this is 6, this is 8. So as the companion gets farther away from the parent star, then we can see fainter magnitudes, which probably makes sense to you. But anyway, so this graph has a lot of information in it. The last thing to say is, what are these colored points? Well, all the colored points are where we have found Kepler stars that have exoplanets where we found companions with our camera. And so I would say that all of these below my hand here and to the left, those are all bound companions. Okay, and in particular, there's this one guy right here, Kepler 437. Kepler 437 is a system that has one exoplanet, but that one exoplanet is basically like the Earth, and it's in the habitable zone. So it is, and yet that system, okay, has a distant stellar companion. Well, I say distant, it's less than 0.2 arc seconds, but you know, and this thing is probably 1,300 light years away or something. So it's, you know, compared to the planet orbit, the second star is way, way out there, you know, like maybe twice the distance from the sun to Pluto. And but it is a planet in the habitable zone. So Kepler 437, well, you guys probably all know what I mean by habitable zone, you know, just the zone, the orbital distance where you can have liquid water. And so that distance changes depending on the properties of the parent star. If you have a cooler star, like an M star, then it's closer in. If you have an A star, that zone is farther out. Well, Kepler 437 is sort of between these two cases. It's a K star. So that's the spectral type in between these two. So you could think of it as sort of in between those two guys. So I want to be clear about one thing, and that is that what I'm talking about here is a star with a planetary system, one or more exoplanets, and then another star far away. I'm not talking about the Star Wars scenario.
I was thinking Tatooine.
You know, which there are examples like that. There are a handful of these guys where you have a very close binary system that maybe has an orbit of days, and then in the distance you have a planet, one or more planets orbiting that pair. Those exist, although they don't appear to be as frequent as the type that I was just talking about. And in any way, and in any case, my camera isn't sensitive to this because that separation of those two stars is way, way too small, even for us, even at Gemini. Okay. So what I'm talking about is this system here. So you would have a star and an exoplanet. So the exoplanet goes around like that, and that way in the distance you have this a second star over there. So if we were talking about Kepler 437, then here would be the sort of the parameters involved here. The planet is about 0.3 AU, but it's a cooler star, so that's still a habitable zone world. The second star is about 75 AUs away. Okay, so the orbital period of that is hundreds of years at least. Okay, and the orbital period here I think is like 66 days. Okay. But how fantastic, right? Like, well, wouldn't it be great to be on this world, right? And then, you know, 66 days is a year, right? Or 66 Earth days is 1 year, once around. And always in the distance, you know, like, so during the day you would see a sun like we do, but at night you would see this honkingly bright star. Actually, if you were here, that star, based on our measurements, would be about as bright as the full moon, but it would be pure stellar, more or less.
That's bright.
Yeah, minus 13. Yeah, and even with a small telescope, you could resolve the disk of that second star if you were on that planet. That'd be pretty good. So anyway, we compile as best we can the results we have on all of these systems, and it seems like we see no difference in the rate of binaries, whether we're talking about stars that host exoplanets or stars that don't. It's the same. It's about, you know, half of the stars that you would look at, they would have a companion either way. Yeah?
I have a question about the relative mass of these two stars.
Yep. So in the case of Kepler 437, the mass ratio is probably around 0.5, you know? I mean, something like that.
What I'm trying to lead is that does the second sun rotate about the first one, or do they actually are both rotating against each other?
Well, it's more like the second case, but, you know, and so, you know, when I was in graduate school, they told us things like this couldn't exist because, you know, this guy had so much there's so much gravitational energy there that that you would change the orbit of this, and over time you basically kick it out. But I think what we know now is that, as long as you're close enough here, that doesn't really happen. So it is like you say, it's kind of one star falling over the other one, but this planet comes along for the ride anyway, and it's fine. And so anyway, so this result is one that was actually picked up by the observatory website. So that's always good when you're a visitor instrument, because it means you probably will get more time. And so we were lucky that they liked what we did there, and so that's why we've been able to keep going back. So I hope we have many more runs out there. But for the moment, the summary on this project is that this Speckle imaging system, which it takes advantage of the ability to get high-resolution images in 2 colors simultaneously, is really the driver behind this type of vetting for exoplanet candidates. It's not the only technique. You got to use a range of techniques, but this is the game that I personally am involved with. And so, but we can use that to study the population of binary stars that host exoplanets versus field stars that host exoplanets. And we find that basically there's no statistical difference between the field sample and the sample where there's an exoplanet. So at least in the range of separations that we're sensitive to, which is not the full range, but for the range that we can see, we don't see a difference. We see in both cases, if you select a star at random, that it has a chance of about 50% of having a stellar companion. So that means that, I guess my conclusion is, we got gypped in a way, right? We're part of the 50% that didn't get that second star. And I've been feeling down about that, but the New Yorker magazine actually had a cartoon, I think it was a week or 2 ago, that cheered me up. Maybe it'll cheer you up too. So it says, the moon saying to the earth, stop complaining, you've got the sun in the morning and me at night. So, and it is true, because the moon, to have a moon that like the one we have is really quite great. It's an amazing thing to have a body that big, right? The ratio between the size of the moon and the Earth is unusually, similar. So we don't have a second star, but we do have a nice constellation prize. So anyway, I think I'll end there so that we can prepare to go out and see and take questions. Okay, yeah.
If on any of these exoplanets that are under some degree of observation, there existed a civilization comparable to our own radio-based technology, would that be observable by us?
Well,
That's
I would
a sad
say
question.
not for Kepler stars. Okay, so the one thing about the Kepler field is that we have, it's actually, if you look at how far away those stars are, it ranges from, sort of hundreds of light years to maybe 2,000 light years, or even more, 3,000 light years. And so, it would take a long time for signals to get here, right? But here's the interesting thing. Now that Kepler has been repurposed, maybe I should say a word about that. Basically, the satellite failed in the following way. It couldn't hold position because some of the reaction wheels failed. I think 2 of them failed, so they couldn't hold position. So the really smart folks at NASA figured out a way to use solar radiation pressure to hold the position for some period of time, something on the order of weeks. And so what they do now is they hold position for as long as they can, and then they sort of reset and look at a new position. And the consequence of that is that you can only look in the ecliptic, because that's the only way the force vectors work out or whatever. And so, but the bottom line is that with the K2 mission, now people are starting to look at systems which are much closer to us, only a few parsecs away, or at most tens of parsecs. So that's a sample of stars which is, sort of more natural for trying to find, civilizations, right? Because we, that distance will be a lot smaller. So the bottom line is Kepler, the original mission, is great for statistics of planets, but it's not very good for communication. And so maybe with K2 we'll find some worlds that are a lot closer. let's see, 1 and 2.
Right. Arecibo will be able to receive its own signal at the other end of the galaxy. So if you were to then point a radio telescope at these systems, you'd be able to pick up signal too. But the other question is, given your diffraction limit and the angles you can see, about how far out physically, I know we always work in angles in astronomy, but about how far out in light years can you go and get these kinds of information before you basically run out of distance of anything meaningful?
Well, I think basically we're okay for the whole Kepler field. I mean, well, maybe I should go back to this plot for a second and just really say what the limit is here. So you can maybe it's a little bit blurry, but all these open points, again, those are physically bound companions in the model. And you can see how they bunch up right towards the diffraction limit. Well, there are even more of them that are over here, which we can't detect, okay? But at least we get enough of the distribution for Kepler, kind of normal Kepler distances, that we can say something about that distribution. So it's almost like saying, I can only look at half of a bell curve. Can I still get the standard deviation? Yeah, I can probably estimate it okay.
So you get, what, 50 to 100 light years?
Well, so Kepler stars are in the range of let's say 500 to 1500 parsecs, so multiply by 3.26, and that's what you got. Yeah. Okay, you.
Yeah, I was just curious when the Kepler was up and running in its full mode, how accurately did it keep itself pointed over time?
It was quite accurate. I couldn't give you a number off the top of my head, but I guess the one thing I could say about that is that one thing that helps is that Kepler is not an imager. Basically, it recorded defocused images onto CCD chips. And so as long as they understood the performance of those chips very well, even if there was some sort of drift of, so basically a star maps onto a huge blob of light that covers many pixels. And as long as you characterize your CCD well enough, if you drift a little bit, you can probably calibrate that out.
Mm-hmm. Okay.
Yep.
About 50% of stars have a binary, correct?
Have a companion.
Companion star,
Yeah.
Now, out of that 50%, how many of them have exoplanets in both companion stars?
Well, that's a question that we don't know, but I would really love to know the answer to that, and if we keep observing, we might get there. But I think the problem with Kepler data is that you really can't tell which star the exoplanet is going around, right? If they're so physically close together. Kepler, you get one light curve for the whole shooting match, and so there have been some papers that have come out that have sort of addressed that point, but I think the answer is not known, which is kind of
Almost like a Mendelian question.
Yeah, exactly. Yeah. Okay. 1, 2.
Yeah, just the binary stars, if the two are too close together, is it not possible to have a stable planetary orbit unless the planet, let's say, is way out?
I think that's true, yeah, that, like if you have the two stars orbiting with a very small period here, then your planet better be pretty far out or it will get affected,
Is there any way to know when the planets were formed and were they formed at a different time relative to the ones in the solar system? Later,
Well,
earlier?
yeah, we can estimate ages of a lot of these stars, yeah, just by looking at the detailed characteristics of how much light they put out in what wavelength ranges. So that's something like, for Kepler stars, there's a list that gives you all those properties, and so an age is estimated. Now, I don't think those are, it's not like accurate to 100 years or anything. It's an estimate, but yes, we know more or less for all of the Kepler stars how old they are.
But that's for the star. What about the planets? Do we know anything?
Well, we assume that they form at the same time.
You think so?
I mean, if they don't, then
That's
I think
a mystery.
that would be a real change of paradigm.
Shall we?
Yeah, I think we
Yeah, let's
have
get
just enough time.
Okay, thank you. Obviously, we can't fit everybody up in the tower, so if you don't know what to do, but I wanted to make sure that Elliott gets up there. Kevin, can you take Elliott up? Sure. Okay, cool. Are you going to try and get an image of this?
It's all set up.
It is. So yeah, it's not going to be viewing through the scope. It's just going to be on a monitor, so there's really not going to be anything to see. So just a heads up. You guys can go up, but there's not much room, as you know.
Also,
I guess,
there's ice on the outside.
oh yeah, it's slippery too, so you got that going for you too. So Eric Raymer is here from Columbia next month. And again, on the 30th, we're going to have the kids up here. So if you're interested in it, come on up. Let's see, what else? I think that's the big stuff. I can't think of anything else. And then telescope training coming up. We'll let you know about that. And that's it. That's a wrap. Thanks, everybody. Thanks for coming out.
I've heard a lot of words that I've never heard before. I've heard second. AU is gold, right? Aerial astronomical unit, right? I don't assume so.
Ours were party yesterday.
I have an envelope if you want to.
Thank God.
Put it in there with that.
Talk about travel.
Yeah, you want, yeah, that's fine.
Thanks, Alex. We're gonna go.
Have your phone on you.
Yeah.
Want to see the big one in the
Yeah, looking forward to seeing you guys out here.
Big one in the what?
No, Bob's right here.
Oh, there's
but-
Bob.
But come back.
Well, anyway,
Yeah,
Bob, let me introduce you to Cole, who's quite interested in astronomy.
Sorry.
And I said, if you'll learn more from Bob in 1 month, then you can. So,
I think I met you two before, Paul.
Yeah.
that's right. Yeah, Caleb Sharp. I knew I'd signed.
I have a solution for our power connector woes, by the way.
Oh, I got crazy woes on this. It sucks.
And power holes.
Oh, really?
Radio stuff, so then you can buy a brick writer and plug anything in.
Shit, that sounds fun. That's
And there's crimpable versions for those volunteers who are not as comfortable with soldering. Some of us maybe.
Yeah, most of us.
Mike, are you a solderer?
We had a
He's
solder.
solderer.
Yeah, we'll take a look.
I heard you might have a torch in your trunk too.
Not my car, my truck.
Yeah. I generally keep a torch available as well.
Cutting torch or welding?
Cutting torch. I had my eye on a plasma cutter. I was trying to pick up. Oh, you did? You have a pull-up machine shop?
I used to. Back in 2011, all that snow we had,
Yeah.
the building collapsed, so I don't have any
We lost
repair.
our own network.
Yeah,
I helped
yeah.
out on a couple of nights.
Yeah.
See, there's how Deborah.
She missed the class. Yeah, taking the class.
I got
Yeah, but I
that.
do have plasma cam still, I have a plasma cam lights, so I do have that.
Which kind?
Another-
What brand is
They
it?
have a training
Okay.
class
Oh, they're nice.
for the volunteers that help
Yes.
on.
Right,
We've been
Oh,
to public.
I went to school to be a mechanical engineer.
We became a double E, right?
But I'm an electrical engineer where I work now. It's
Yeah.
really not electrical engineering work I do, it's really,
Opening and
when I work at Norden, I know it's